Okay, I think it's going to work.
Yeah, I think so. Do you want to wait for Bordeaux a little bit, or it's weird? I think they're not around.
Mm-hmm. Okay, we're online.
Oh, we have two Stephanies.
Why there's two Stephanies? Um,
Okay, I think it's working. I think we are online.
yeah, I think you should start. I mean, hi everyone. Sorry, we had some technical issues, but now everything is fixed, and now it's Monday and Neuroccino time. And today Eduardo will present, I think, an exciting paper. So you can share your screen and we can go
Yeah.
ahead.
So let me share the link again. Okay, should be able to see my screen.
Yeah, I see it.
Yeah,
Perfect.
okay, it's good enough. Yeah, okay. So let's get started. An exciting paper. Yeah, I hope so. It's a review paper, so maybe a bit unusual for Neuroccino. I don't have a lot of exciting images, which maybe it's a poor choice for me presenting, but I think it's an interesting paper. So it's a sort of like a 25 years anniversary review paper for this asymmetric sampling in time hypothesis. And for those that other people are joining. And for those that you don't know what this is indeed an hypothesis concerning the language lateralization. Actually, not only language, but more like auditory processing lateralization in the brain. Developed some, yeah, almost 25 years ago, firstly proposed by David Poppel. And now, yeah, they put forward this review to kind of test and check whether like the evidence that has been accumulated in the past 20, 25 years is in favor or against this hypothesis and what can be done to push it forward. Um, so the very core idea of this hypothesis is that, and what it proposed, and is a sort of like division of labor between the two hemispheres, with the left hemisphere auditory areas, especially secondary auditory areas, having a specific short integration window for processing acoustic inputs, sort of like something in the span of like 20, 25 milliseconds. And for this reason, being mostly suited for rapidly changing signals. And on the other side, the right hemisphere auditory areas being more specialized in processing along a long integration window in the order of 150, 300 milliseconds, making the right hemisphere theoretically more suited for slowly changing signals. Um, and yeah, one of the assumption, and this is one of the figure that I can show you, is that of course, the auditory processing is bilateral, especially at the very beginning of the Marcel is coming. Of course, at least at the very beginning of the processing, and yeah, this is just a neurosynth like image to demonstrate that speech perception is kind of bilateral. There's no point in assuming a strong lateralization for a speech perception, like an absolute lateralization in which like the right hemisphere is doing nothing. It's more bilateral, so that the point is trying to explain why this happens and how this happens and whether there is a reason for information being processed either in the left or in the right hemisphere. But yeah, so this is kind of the introduction, and there is like then a more like a second paragraph titled "What is right, what is left," that is doing a little bit more, is going a little bit more in detail in this kind of like trying to explain what is supposed to be, so that the left hemisphere, okay, does prefer, according to this hypothesis, rapidly changing signals, which means, for example, like subsegmental features of speech signal, like form and transition and burns, like fast burns in the speech signal. Rapidly modulated frequency signals, and the right hemisphere is doing exactly the opposite, preferring like slowly changing signals, like suprasegmental features of speech, such as like a phonetic stuff, and even higher, like say prosodic structure and so on. The overall point, however, is just like, because we might ask like, what's the point of having such a division of labor? So the overall point is that this division might be like, it might be as like an evolutionary solution, like an evolutionary like advantage, so that the brain in this way might be able to deal with the uncertainty principle that concerns time frequency resolution. And then we know that in or it is hypothesized that the auditory cortex is decomposing the auditory signal in a time frequency structure. And the problem is that if you know something about like signal processing, you cannot have an infinitely good resolution in both time and frequency. You always have a trade-off. If you have a high frequency resolution, you cannot have a good time resolution, and if you have a good time resolution, you cannot have a good frequency resolution. And dividing the processing of information in this way might be a way to kind of boost both things in an optimal way. And yeah, and what follows then in the next paragraph is and is kind of summarized in this picture two. Let's see if I can make it. Yeah, is like a relatively linear and clear review of the evidence in favor for this hypothesis for the right hemisphere, and the evidence against the right hemisphere, for evidence against this hypothesis for the right hemisphere, and the same for the left hemisphere. And like, to cut it relatively short, what they did is they investigate, like they picked up different papers using different stimulus type, temporal extent of the stimuli, task engagement, and modality. And what this panel B is supposed to represent, it's not super immediate, but it's supposed to be like the amount of evidence in favor of the hypothesis for the right hemisphere and for the left hemisphere, for the different like things they looked at. And what you can observe, what they put forward, is that this hypothesis for the right hemisphere is kind of well supported. So there is a lot of evidence pointing to the fact that the right hemisphere might be dealing with slowly changing signals in time in terms of auditory processing. And this evidence is relatively stable across stimulus type, temporal extent, engagement, and modality. The same cannot be said for the left hemisphere, where the evidence is basically more mixed, and there is no strong, like the hypothesis seems not to hold very well for the left hemisphere, because basically you have the papers, experiments like showing that yes, the left hemisphere might be processing like fast changing information, but then you also have other papers showing that might be bilateral, might be the other way around. So this kind of hypothesis is not stable for the left hemisphere, and so what they focus on is mostly the right hemisphere, and why this might be like why there might be a reason for the right hemisphere to process slowly changing information. And there is also a small, well, not small, but there's also a section on evolutionary things, I would say, like, yeah, asymmetric sampling and evolutionary continuity. The whole point, and they go through like some evidence from like rodent study, birds, bats, and like non-human primates. I won't go into the detail too much. That the whole point of this section is to try to show that this kind of adaptation that it's supposed to be in the human brain, it's probably not unique to the human brain, and it was possibly evolved either before we split for our last common ancestor with apes, or that most likely it was a solution that has been adopted multiple ways across the branches of evolution. So it's unlikely to be human specific, and this kind of differential processing across hemispheres is something that we observe not only for acoustic processing, but for a lot of stuff. Also in other species that are very, very far from us, like birds. But yeah, so the last section, like the last important section of the paper, as I mentioned, is trying to wrap up a story around this. Like 25 years of like a new evidence for this symmetric sampling in time hypothesis, and this, yeah, they focus basically on the right hemisphere because this is what seems to be fairly stable, like across the literature. So the important questions at this point will be like, what is special about the right hemisphere, and what is special about slowly modulated information in the auditory domain. And yeah, as I mentioned, this structure might be helpful to overcome the limitation of time frequency decomposition for auditory signals. And what they mentioned, but this is something I would like your opinion, your ideas on, is that there seems to be a discrete amount of evidence for micro and macro structural connectivity patterns in the right hemisphere that might favor this way of processing information in the right hemisphere, with a sort of like less structured connectivity, but more widespread connectivity in the right hemisphere. Then, like, according to what they say, should allow the right hemisphere to keep a more sustained and long windows of processing information, which is what is required to kind of have like these long integration windows. But yeah, I mean, if you have more to say, that would be interesting. But yeah, so the kind of conclusion is that if this holds true, then the right hemisphere is basically exactly as efficient as it needs to be to represent a specific kind of information, as they put it, because it's not a hemisphere that is like non-dominant for language. It's just doing a kind of processing that evolution kind of prepared it to do. But yeah, there is also like tons of like ambiguous evidence. They mentioned, for example, the still unsolved problem of inter-individual variability, which is made even more complex by the fact that the structural and functional lateralization is often, like, they often seem not to go directly hand in hand. There is top-down modulation provided by linguistic features that we don't know exactly how they interact with the input. So when like there is a specific language feature at play, it seems that this pattern is a little bit broke down. And yeah, what else? Yeah, there's still a lot of unclear things, for example, about the pattern of lateralization. Like you might observe, for example, for some structure in the temporal gyrus, like the Heschel gyrus, the Heschel circles, the plano temporale. If you look at different metrics of like brain morphology, brain structure, like the cortical volume, cortical thickness, and surface, like not even looking at the white matter, just staying on the surface, you see that you have a really, I had to say, like, weird, not weird, but like a really complex pattern of lateralization, depending whether you look at the cortical volume, the cortical thickness, and the surface areas. And it's not clear what is relating to what is causing what. You also have different, apparently, columnar organization in the left and right Heschel gyrus, which is the lower panel, with the left Heschel gyrus having like a more widespread like columnar organization, while the right hemisphere having more like compact organization. but then it's not clear how each of these variable relates, whether it relates to language lateralization. So it's a bit complex to figure out what exactly is going on. So yeah, then there's also the question of the intra-hemispheric connectivity. So if the right hemisphere is doing language, then what happens? Is it being like transferred to the left hemisphere? Is it kept for more processing in the right hemisphere itself, and so on, and how information is integrated? So yeah, this was in a very, very short presentation, like the asymmetric sampling theory for auditory processing. And yeah, the main conclusion is that it seems to hold for the right hemisphere. So that it's likely that the right hemisphere is more suited for processing information, auditory information, on a relatively long time, like an integration window. Doesn't hold so well for the left hemisphere, but yeah, there is a lot of confounding factors from like language top-down modulation, from inter-individual variability, and so on. But yeah, I was wondering, like, whether you have ideas, opinions, especially for what concerns the wide matter at the macro level, of course, like the one we deal with. And yeah, that's it. I don't have any more images.
That is fine. It's not necessary to have images to talk about the paper. So thank you for presenting this. And if anybody has any questions, you are welcome to ask them. So if not, huh?
There is an incognito staff now in the chat.
Well, I have a question.
Yeah.
It's not really clear for me. What do you mean by that the right hemisphere is for processing long modulated signals, or what? Can you give like more specific examples? What type of information, according to this paper, it processes?
Yeah, okay, yeah,
Like,
sorry. Yeah, okay, I'll try to make it more clear. So, first of all, the hypothesis is not only about language, it's about like auditory signal in general. So the evidence that they put forward is also coming from like experiment using auditory stimulation that is not language. But that's another point. What you should keep in mind is that so we think that the auditory cortex, primary and secondary, and then moving on to more complex areas, is starting from a time frequency decomposition of the signal. So the incoming signal is a time evolving signal, waves basically, that are recorded in the ear and that they travel to the auditory cortex. What the auditory cortex is maybe possibly doing is a frequency decomposition of this signal over time. And the point is that to do this kind of decomposition, so if you want to like decompose the signal into frequency, you need some time extension. And the extension of these time windows is, I think, what they refer to as integration windows. So it's, for example, I don't know, if you're doing like a MOLED wavelet deconvolution, there will be, I don't know, the width of the Gaussian on which you're integrating your signal. So like examples that they put forward is like a slow integration, like a slow integration windows is like what would allow you to pick up relatively low frequency stuff happening in your, say, language or speech signal. So like pick up information in the incoming signal that is relatively slow, for example, at the syllabic rate, or even slower at the sentence level, for example, prosody. Which at least for languages like English or like Latin or European languages is we don't have like tonal language. No, we do have some tonal languages in Europe, but anyway, for non-tonal language, like the only modulation that you have is the prosody modulation, for example, and this is relatively it is a low frequency signal, right? Because it's evolving over like a long period of time, and you have like sparse information, and you need a long integration window to pick up that signal. Because yeah, how can you do if you have like a very short integration window that is like much shorter than the information that you're trying to process? Then you cannot pick up the information itself. But on the other side, for language, you also have like a very fast information that is happening, yeah, in the span of like a few milliseconds. So yeah, you have to like, especially some, yeah, well, they provide some examples here. Rapidly changing signals in the left hemisphere, for example, subsegmental features of speech signal, like yeah, Foreman transitions, and rapid frequency modulated sweeps. So that would be like features of the signal change that change like very fast in time, and then you can allow a short integration windows because you're not really interested in the time domain, but you're more interested in like in having like a good frequency resolution. But you cannot have both. So one way to deal with it is to have an hemisphere more specialized on one kind of information processing, and another hemisphere doing kind of the opposite. Is it more clear?
It's becoming more clear.
Okay.
So, but for example, so yeah, you say that the right hemisphere is more like prosody because it requires long integration
Yeah, this is an
windows, right?
example.
So, would you then expect some differences in functional specialization between, let's say, European languages and languages like that heavily based on uh,
Yeah, like tonal
intonations?
languages. Yeah, that's a
Yeah,
good idea, and
exactly. So
it's
then, would you like neurosynth, I guess, has most of the data based on European languages. So I would guess, I don't know. So
I
what
don't
do
know
you think
neuroscience,
about
but
this?
this
And
is a line of research that has been investigated. I don't know how like I never went like deeply into it, but one of the point is that some people uh, try to themselves like there is some data, so some labs show that it's possible that when you have tonal languages where like the tone is a lexical feature, then this kind of processing is shifted toward the left hemisphere.
Mhm.
And this is related to the like top-down modulation I was referring to before, and they talk about it in the paper because it's really hard to tease it apart. Like because this hypothesis was developed for the incoming inputs at a relatively low level, like first, secondary auditory cortices. But then you have these linguistic features for a language using like tones as a lexical feature, like to discriminate between words. Then it seems that there is more left lateralization for the tone feature itself. But it's also hard because then it's happening at a smaller scale itself. When you use tone as a lexical feature, it's happening at the word level, but you use prosody, it's usually on the sentence level. So it's a longer time windows anyway. So that's even one more confounding factor. But there is some data if you want to look into it, like proposing this idea that when you use like some tonal features for lexical discrimination, then it's happening more in the left hemisphere, and when it's more prosodic or like really suprasegmental, it's happening more in the right hemisphere. This might still hold with this asymmetric sampling hypothesis, but yeah, I don't know the details. So,
Mhm.
but
Yeah,
there is
yeah.
stuff on it. Yeah.
Okay. If no one has any other question, I have another one.
Uh-huh.
Since we started a little bit later, can you go down when you are talking about the structure of the Herschel gyros, like, yeah, that image? So I was just wondering, like the image B,
Yeah.
actually C, I was wondering. So you mentioned a little bit of inter-individual variability. Do they mention in the paper that it can happen that in some participants you see or patients, or I don't know if it's post-mortem, I guess. So if you have opposite pattern of the columns of the planum temporale,
I'm not sure they
is it
meant.
always like this? Is it like a fixed structure for all the
I think
um,
they presented some evidence from a group level kind of stuff. I'm not sure they go too much into details about this stuff because I'm not even sure there are studies trying to look at the inter-individual variability on this level of precision. But yeah, it's one thing they mentioned that might relate to this is that there is a lot of uncertainty about the relationship of this kind of asymmetries with the language lateralization at the functional level. So
Mhm.
it's like, yeah, sometimes we find correlation with the language measures of language behavior, sometimes we don't, sometimes we find the reverse pattern, so like contrasting findings. Sometimes we find a correlation for the
Yeah,
volume,
yeah,
sometimes for the surface. It's not even clear,
yeah, yeah,
right? It's
yeah.
like handedness as a and language, like the seems to be go hand in hand. And if you look into it, it's kind of a mess. Um, so
Yeah,
yeah,
no, I was just more wondering without touching the functional space, just pure anatomy, if there are cases where you have the opposite situation. And also, Stephanie from the chat says that anatomically you have one or up to three Herschel gyri actually, and she was wondering how does this fit with this review to have more than one Herschel gyri anatomically. So
yeah, I don't think they mentioned
uh,
directly the
yeah.
gyral structure.
So they
Um,
were more talking about the variability between, like, in correlation between function and structure rather than
yeah, also that, yeah, also that.
yeah. Okay.
But what they looked at for the actual gyros is mostly volume, thickness, and surface, um,
Okay.
which is
Hmm.
already kind of
Okay.
relative. Well, it's not a mess, but it's complex anyway already.
Yeah.
But yeah, I
Mm.
think there are though people with like a reverse pattern of purification, but yeah,
Yeah.
I'm not sure
Okay.
about the columnar structure.
We have two more questions. So I think Fernando was the first.
Yeah.
You can ask a question.
Yeah, thanks, Edo, for the nice presentation and a nice paper. I had a question, a bit more of a general question. How do you think this paper challenges or adds some nuance to the view that the language is left lateralized in the brain?
Uh, uh, I mean, if you look at the past, like the idea of language being strongly like left lateralized with the right hemisphere doing basically nothing, I think that doesn't really hold anymore, but it has been a while since people realized that the right hemisphere is doing stuff for language anyway. Um, so is this like your question? Like you mean like
Yeah, so there seems to be adding different, well, at least splitting different functions into one hemisphere or the other because of the different temporal windows of processing
yeah,
information.
yeah, okay, yeah, okay. So I mean, if you just think about the auditory input itself at the very low level, this is happening in both hemispheres anyway. So the question is not whether like language is starting to be processed in one hemisphere or the other, but at, if you really want to push like a strong lateralization hypothesis that you should explain how the input that is being processed, say in the right auditory cortex, is then being sent to the left hemisphere, for example. So what we know is that at least at the very first steps, there is like a bilateral organization. on the functional level and also the structural level. But I think like also like lesion studies or like patient studies can show you that as if you have like a well-structured, say, perisylvian white matter in the right hemisphere that is helping you to recover from aphasia, because one of the probably one of the stronger evidence for language lateralization is that the fact that you have a lesion in the left hemisphere, then you most likely have that's like some sort of like aphasia, which is true. But then the whole thing is often like intertwined with like production paralysis, what is actually language processing that is being like damaged, and what is more like kind of production aspects. So I think this paper doesn't really go too much into challenging like left lateralization itself. It kind of assumes that language is being processed largely bilaterally, and that we might observe like some lateralization for some aspects of language, but in the left hemisphere, but we might also observe like the reverse pattern of right lateralization for some aspects of language. And giving this hypothesis of asymmetric sampling in time, what you would observe in the right hemisphere is this kind of like slowly modulated information processing. I hope that answers. Yeah. Think we are deleting.
Yeah, we got 3 minutes, so two
Yeah, we
quick
were a bit late,
questions
so it's
for
fine.
Liting and Fernanda. And yeah, Liting, go ahead.
Yeah, I remember you mentioned that the right hemisphere, like from the study, it says the right hemisphere has more microstructure spreading out in the white matter. I remember vaguely you say something like that. Can you elaborate more, or maybe I misheard?
Yeah. Yeah, this is something they mentioned. Yeah, they mentioned something about the organization of.
Yeah, like what do you mean there's more spread out in the microstructure in the right hemisphere?
Yeah, this is something I hope to have your feedback as well, because it was not super duper clear to me what they meant, because they review some evidence about the microstructural and also more macro level, like macrostructural connectivity in the right hemisphere. What they mention is that there might be a pattern of connectivity that allows the information to flow for a longer time in the right hemisphere. But yeah, that said, I'm not super sure about how. So one thing that they say in the paper is like, there's this paper, they report this paper finding that the right hemisphere and its white matter network display less global and local efficiency, as well as more random configuration, which I'm not sure what exactly means. These properties speak to a decreased efficiency of parallel processing. However, at the same time, a higher betweenness centrality, totally unclear what this is, indicates that the right hemispheric white matter network allow a higher degree of information flow compared to the left hemispheric network. Yeah. This translates to the functional connectome as well, where it has been observed that the right, as compared to the left superior temporal cortex, is characterized by a higher density of short and long range functional connectivity. So yeah, what I get from this section is that there is something, according to the evidence that they review, that allows for like a larger information flow in the right hemisphere, but I'm not super clear why that will be the case, at least at the macro level of structural connectivity. So
Yeah, I guess we will need to read deeper the paper to understand maybe what they meant by this. So
yeah.
And
I mean, I didn't go
Fernanda,
into the references, but
Yeah.
you know.
Hello.
Makes sense. Yeah. And Fernanda's question?
Yeah.
Yep. Hello. I was just wondering about the. It was not very clear to me that they take interindividual variability as like a possible confound for their study, but then it was not very clear to me what kind of data then they're analyzing. I guess a lot of like meta-analysis of neuroscene plus the data that they found in repositories to be able to do these like cortical thickness differentiations. It's just like unclear to me like the kind of data that where did they get it from, and how, if they do say something more about the interindividual variability.
Yeah, okay. Yeah, sorry, I should have mentioned maybe more clearly. The neurofint meta-analysis here is just an example they put forward. But most of the paper is, yeah, it's a review. It's not even in the title, sorry. It's a review paper. So they mentioned they looked into some specific stimulus type, temporal extent of the stimulus, task engagement, and modality. But it's not a meta-analysis. There is no systematic search of the literature. So yeah, it's just the authors of related to these hypotheses, like kind of reviewing the evidence like 25 years after it has been put forward. So it's more like an author review. It's not systematic. It's quite. I mean, I don't know the field too much, but it's quite well organized. There is no evidence in favor and against one hemisphere and the other, and yeah, it's that part is relatively easy to follow, and one can dive into the literature of the report. But yeah, and for the confounding factor of the like a group individual level, like individual variability and so on. There is like a paragraph on it. It's mostly a paragraph to put forward this limitation that we are starting to address maybe in the last few years, but there is a problem that for a long time neuroimaging studies basically focused on like a group level, and individual variability was considered more like a confound than something interesting. But then they mentioned like a couple of studies where they actually tried to look, for example, like how many participants did show this pattern that we found at the group level, and then you see like, oh, maybe 60% of your like participants are showing this effect, but then they have like some 40% this showing something else. So you have this problem that you in the future should be addressed, where you might have a group like level pattern that is reliable, sure, that's interesting as well. But you should maybe also take into account the fact that each individual in your experiment might actually exhibit like a complex pattern, and that might be actually, that is not noise, that is actually useful information that you might use to kind of figure out what the hell is going on in the brain. So yeah, I hope that answered at least partially your question.
Okay. I think then that's it for all the questions.
Yes.
And thank you, Eduardo, for presenting this paper, and everybody for participating and joining us today. So see you next week, and have an exciting weekend, science. Bye bye.
Bye, guys.